Aerodynamic development and lap time simulation are key to improving and understanding race car performance such that information on these topics is kept highly secretive in racing. The UNCC Aero senior design team successfully developed an open-source lap time simulator and aerodynamic development methodology. The method and tools were validated by implementing and testing them on a short-track race car that was donated by a local race team. Vehicle aerodynamics and lap time simulation are extremely intertwined, as a lap time simulator can be used to determine what aerodynamic configuration gives the car the quickest lap time per track. The lap time simulator was developed in MATLAB in a modular style, allowing the mathematical models to be modified or improved with ease. The dynamic bicycle model uses a quasi-steady-state approach and is capable of solving for aerodynamic characteristics to achieve the quickest lap time, or for the lap time based on given aerodynamic characteristics. The model can be applied to any vehicle or track by simply uploading the relevant data through the Excel-based user interface. With pre-existing track data for this test car, the lap time simulator's predictability was partially validated early on, allowing us to use it as a development tool. The lap time simulator was used to analyze the test vehicle on various tracks, allowing us to determine and design towards the most beneficial aerodynamic characteristics. Using computational fluid dynamics, or CFD, the vehicle's aerodynamics were tested and improved by designing aerodynamic add-on parts. Over 30 parts were developed in CAD, and over 120 simulations were run in CFD, which narrowed down the most optimum vehicle configurations. Our team was supported by the UNC Charlotte Department for Motorsports and Automotive Research. Though this meant our team didn't have a conventional budget, it allowed us to use department-specific resources and connections which were critical to our project. With the budget limitations and the core purpose of this project, prototype parts were built to function in testing and not for long-term use. The most notable component to this project was the actual implementation and validation through wind tunnel and on-track testing. Full-scale wind tunnel testing provided a physical, real-life measurement of the aerodynamic performance and a rare opportunity to compare and validate our CFD results. The car was taken to Aerodyne's A2 wind tunnel in Mooresville, North Carolina, where a total of 18 configurations were tested. All of the best parts, as determined in CFD, were added to the vehicle one by one. The splitter and the spoiler sensitivities were studied, and various development runs were also done. In the wind tunnel, we saw a downforce gain of 1,054 counts, with a drag penalty of only 426 counts, which differed from our CFD by under 5%. We increased our aerodynamic efficiency from 40% to 85%. We were able to determine a range of aerobalance options between 35 and 55% front, which was a major improvement from the baseline 91% front. The lap time simulator was intended to be validated through straight line and dynamic track testing. This was a major key to understanding both the performance gain of the aerodynamic package on track and also our lap time simulator's ability to predict the change in lap time based on the change in aerodynamic configuration. Sadly, due to the coronavirus, our team was unable to execute this component of testing and correlation. Despite the lack of track testing, our team produced proven aerodynamic gains that correlate well to CFD and a fully functional lap time simulator that is capable of predicting lap times within 5 seconds. By publishing our methodologies, data, analysis, and the various custom tools we developed throughout this project, we hope to help future students and researchers by filling a major gap in literature that's currently available.